So, so today we look at the first subtopic for radioactivity. Okay, now, so first we look at the, we learn in chemistry also. So you look at the atomic model. Now, basically, atom consists of nucleus. Okay, so the nucleus consists of proton and neutron, and then you have electron orbiting the nucleus. Okay, so you have electron orbiting the nucleus. Okay, so this is the atomic structure. So and then okay, so the nucleus in the middle consists of proton and neutron, and then you have electron orbiting the nucleus. We have electron orbiting the nucleus. Okay, and then okay, this one also from chemistry also. Okay, so when you write your element, right? Okay, let's say the symbol of the element is X, so there'll be two numbers on the left hand side, one at the top and the bottom. Now the top one we call it nuclear number. Nuclear number is number of proton plus neutron. Okay, the bottom one we call it atomic number or proton number. Okay, atomic number or proton number, which tells us about the number of proton. Okay, the number of proton Okay, that means let's say if you have element Y, right? Okay, let's say here 24, here is 6. Okay, so basically number of proton will be 6 and then number of neutron will be 24 minus 6. Okay, so 18. So if they ask you how much is your electron, electron will be 6. Okay, electron will be 6. Okay, now let's say if it's in an ion so let's say this is positive 2. Okay, so the number of proton is still 6. The number of neutron still 18, but the number of electron now becomes 4. Okay, that means you reduce by 2 Okay, that means only the electron goes out and comes in. The proton remains the same. Okay, same also let's say if this one is negative 2 ion, right? So your proton is still the same. Now what happens is you have more 2 electron compared to proton. Okay, so meaning here will become 8. Okay, it become 8. Okay, now next we look at isotope. So isotope basically, right? Atoms, right? With the same proton number, different nuclear number. Okay, so atom with same proton number, different nuclear number So example like hydrogen, right? So you have the same proton number but different nuclear number. Okay. Now next we look at radioactivity. Now radioactivity is defined as okay, spontaneous and random decay or disintegration they call it. Okay, spontaneous and random decay of an unstable nucleus into a more stable nucleus. Okay, accompanied by emission of radioactive ray. Okay, accompanied by emission of radioactive ray Okay, so basically you have unstable nucleus will decay to become more stable, and then what happens? It will emit radioactive ray. Okay, or radioactive radiation Okay, radioactive ray or radioactive radiation. Okay, now so this process is called spontaneous. That means it happens by itself. So it's not influenced by physical factors such as temperature, time, pressure. So it's spontaneous, happen by its own. Okay. Now and then it's also known random because each atom has the same probability of decay. Meaning like this Let's say if you have a radioactive element, so inside the element there's a lot of atoms. Okay. So let's say inside the element got a lot of atoms. Okay, so all these atoms has the same probability to decay or disintegrate. Okay, that means doesn't mean the atom at the top must decay first. No. So all these atoms can decay first. Maybe this one can decay first, this one can decay first, this one can decay first. That's what they mean by it's a random process. Okay, so all the atoms have the same probability to decay. Okay, now next. Now, so basically, right? When the unstable nucleus decay to become more stable, it will emit radioactive radiation. Now, this radioactive radiation can be, we can have 3 types of radiation. One we call it alpha particle. Okay, alpha particle. Okay. Second one is beta particle. and then this one is gamma ray. Okay, so now, so it can emit alpha, beta, or gamma. Now, sometimes what happens, it only emit one type of radiation, let's say alpha or beta or gamma. But sometimes it can be combination of two, let's say alpha, beta, beta, gamma, or whatever. Or it can emit three type one shot. Okay, so it depends on the element lah. Okay. Okay, next we're going to look at what is the characteristic of alpha, beta, gamma. Now, alpha is a helium nucleus. Okay, helium nucleus. Alpha is a helium nucleus. So alpha, there's another symbol. Okay, for 2 helium, or this is a symbol for alpha particle. Okay, like A like that, alpha. So alpha, you can use this symbol of 4 2 helium. Now, beta is fast moving electron, fast moving electron. So it can be 0, -1 electron, or the symbol is like B, beta. And then gamma is a wave. So gamma has no proton number, there's no neutron number. So gamma will be this symbol. Okay. Now next, we look at the charge for alpha, beta, gamma. Now alpha is positively charged, beta is negatively charged, gamma has no charge. That means gamma is not neutral. It has no charge because it's a wave. Okay. And then we have mass. Now, in terms of mass, alpha has the bigger mass among the three. Okay, gamma has no mass. Now, why alpha got bigger mass? Because alpha is, okay, what do you call it? Is positively charged. So, positively charged is much more heavier. Okay, so alpha is much more heavier because alpha is the nucleus. So, beta, because it's electron, so it's lighter. Okay, next we look at okay, in terms of speed, right? This one related to mass lah. So we know that alpha got the bigger mass. So in terms of speed, it's slowest. Okay, beta will be moderate, gamma will be fastest because gamma is a wave. Okay, gamma is a wave. And then ionizing power. Now, what is meant by ionizing power or ionization? Okay, now let's say these are air molecules. Now, initially the air molecules are, what do you call it? Are neutral. So let's say alpha, beta, gamma, when they travel, right? So they experience collision with the molecules. Okay. So initially what happened is, let's say this atom, right? So you have nucleus and then you have electron orbiting the nucleus. Okay, so you have electron orbiting the nucleus. So what happened when alpha or beta travel, right? They hit the first molecule. So because of the impact, what happened? The electron from this molecule can come out and then jump to the next neighboring atom. So what happened? This one loses electron, so become positively charged. Okay, because you lose electron, right? This one you gain electron, become negatively charged. So this is what we meant by ionization. That means when alpha, beta, gamma, they travel in the air, they experience collision because with the air particles or air molecules. So because of that, what happened? Ionization will happen. Okay, ionization will happen. Okay, now in terms of ionizing power, that means ability to make ions more you will see that alpha has the strongest ionizing power. Okay, because it got bigger mass so the impact is more. And then beta have medium, gamma has the weakest ionizing power. Okay, now in terms of penetrating power, okay, so alpha will be the lowest, gamma will be the highest. Okay, why alpha penetrating power is less? Because most of the energy is used for ionization just now. Okay, most of the energy is used for ionization. Okay, now so usually we use this diagram to show the difference in penetrating power, right? Okay, sometimes okay they use your hand, your skin your hand, the skin, or sometimes they use paper. Okay, paper you have aluminium with 3 mm thickness, and then lead So you look at alpha, right? So alpha cannot penetrate our skin. Okay, so alpha cannot. Okay, so it can be blocked by our skin, can be blocked by paper also. Okay, whereas beta can penetrate our skin, paper, but can be blocked with aluminium with 3 mm thickness. Okay, 3 mm thickness. Okay, that is for beta Okay, now gamma, so it can penetrate. Okay, and then it can penetrate the skin or the paper. It can penetrate the aluminium. Okay, but when lead, right? If the lead is not too thick, what happens is you see there'll be a reduction in the energy But if the lead is thick, it can block. Okay, let's say if the lead is thick, it can block the gamma ray. Okay, so this case because it's 3 centimeter. But if the lead is very thick, it can block the gamma ray. Okay, but in this case, you can see that the energy being reduced lah after this. Okay, that's why lower amplitude. Yeah, if the lead is not too thick. Okay, so we say that okay, what do you call it? Alpha lowest penetrating power, gamma has the highest penetrating power. So that's why, right, usually when we want to make container to keep radioactive material, we use lead. Okay, because if the lead is thick enough, it can block gamma ray. Okay, so we use lead, okay, to keep or to store radioactive material. Okay, next we look at range in air. Now, range in air meaning how far they can travel. So in terms of this tree, right, you see alpha can only travel a few centimeters. Why? Because it has not much energy. Most of the energy is used for ionization. Okay, beta can travel slightly further, few meters. Gamma, okay, can travel, okay, few hundred meters. Okay, so gamma can travel the furthest. Okay, why? Because gamma has what they call it, highest energy lah. Okay, now effect of electric field. Okay, effect of electric field. So if you see, right, yeah. So let's say you have electric field, right? Okay, so what happened when we fire alpha, right? So you see that alpha will be deflected towards the negative plate. Okay, alpha will be deflected towards the negative plate. Okay, so why is alpha deflected towards the negative plate? Because alpha is positively charged. Okay, alpha is positively charged. Okay, what happened when you fire gamma? So when you fire, beta, you see deflected towards the positive plate. Okay, because it's negatively charged. Okay, and then one more thing when you draw, right? Since alpha has smaller, alpha has bigger mass, beta has smaller mass. So beta is more curved. Okay, beta will be more curved lah. Okay, compared to alpha. So other than direction, you have to look at the curving. So the curving will be more for beta compared to alpha. Okay, gamma will travel in a straight line. Okay, because gamma has no charge. So gamma won't be deflected. Okay, so gamma won't be deflected. Okay, now the last part is the effect of electric field. Effect of electric field. So alpha beta will be deflected by electric field because what they call it, alpha beta are charged. Okay, gamma they won't be deflected. Okay, they won't be deflected. Okay, why? Because gamma has no charge. Okay, so when alpha beta gamma, sorry, when alpha beta travel in the magnetic field, alpha and beta will be deflected. Okay, let's say this is your magnetic field. So alpha in this case is traveling downward. Okay, this one actually, right, supposed to be, yeah. So this one is magnetic field. Magnetic field into the paper. Okay, into the paper. That means the magnetic field is going in. So direction of magnetic field is going in. So when you fire alpha, you see that for this example, alpha will deflect downward. Okay, beta will deflect upward. And then beta will deflect more because of the mass, smaller mass. Okay, the thing is how to determine the direction of deflection. Okay, how to determine. Okay. Okay, let's see, right? This one shows the magnetic field going into. So what do you have to do? You have to use your Fleming left-hand rule. So this is alpha, so alpha is coming here. So for your Fleming left-hand rule, right? If you remember, right? So this one is force, magnetic field, current, FBI, FBI. Okay, so okay, okay. Just now it's wrong. Just now it's going out. Yeah, this one is out actually, not in. Sorry. Okay, this one going out. The magnetic field is going out, not going in. Sorry. Okay, so magnetic going in. Okay, so what you must do is, okay, first, okay, so this one, right? Okay, first you have to show your magnetic field going, this one, going out, going out. So that means pointing outward. Okay, and then this one direction of alpha. So alpha is traveling this way. So what happens? You have to turn this way. So you can see, right? Alpha go this way, and then your magnetic field is coming out. Okay, magnetic field is coming out. Okay, this one is going this way. Alpha going this way. Alpha, you follow the current. Alpha, you follow the current. So that's why it's deflected downward just now. So alpha will deflect downward. Okay, alpha will deflect downward. Okay, but why beta will go up? Okay, now if you want to find for beta, okay, beta is the flow of electron. That means electron move to the right. If electron move to the right, okay, electron move to the right, that means your current will move to the left. Okay, electron move this way, that means current must be opposite. So that means when you use Fleming left-hand rule for beta, right? Okay, so your magnetic field is still going up, correct? Going up, and then this one, right? Okay, points towards. That means if beta moving this way, that means your current must be opposite. So you can see the current is opposite. So where's your force? Force is upward. So that's why beta goes up. Okay, that's why beta goes up. Okay, so this one you have to use your Fleming left-hand rule. Okay, so dot means coming out, cross means going in. Okay, so for this example, the magnetic field is going out. Okay, and then your beta moving to the right, that means if beta electron to the right, that means current to the left. That means that's why I point this way. That means it will deflect up. Okay, actually, if you know alpha down, beta will be up because it is what they call it. It is in the opposite charges. Okay, but when you draw, you make sure beta is more curved compared to alpha because of smaller mass. Okay. Yeah. Now next we're going to look at more on the equation for alpha decay, beta decay, and gamma decay. Now let's say if we have an element X, before the decay, we usually call it paranuclide, and then this element decays and become a new element. Let's say Y, we call it daughter nuclide. So and then it emit alpha particle. Okay, alpha is 4 to helium, right? So you will see what happened to the number of proton and number of electron, number of proton and neutron number, right? You see that your proton number will decrease by 2 in alpha decay. That means if this one is Z, here will be Z minus 2. So that when you plus back, right, Z minus 2 plus 2, you get back Z. Example like this, like uranium, right, 92, okay, decay become thorium and emit, what do you call it, alpha particle. So this is 92, right? So this is 90 plus 2. So 90 plus 2 get 92, so balance back, okay? Whereas your nuclear number will decrease by 4. So that A minus 4 plus 8 got back A. That means one is 238, 234, right? So 234 plus 4 get 238. Okay, so that means for alpha decay, proton number decreased by 2, neutron number decreased by 4. Okay, now how about beta decay? Now for beta decay, let's say if element X decay become Y and then emit beta particle. Now see, the beta is 0, -1 electron, right? So what happened to your proton number? Your proton number will increase by 1. Okay, increase by 1. That means Z plus 1 plus -1. Okay, you get back Z lah. But your nuclear number okay, does not change. Okay, nuclear number does not change. Example, okay, strontium decay become yttrium and then emit beta particle. You see, here's 38. So here's 39. So 39 minus 1, you get back 38. 90 plus 0, you get back 90. Okay. Now the question is, how come, right? Your proton number increase by 1, your nuclear number doesn't change. Okay, because we know that nuclear number, okay, equals to number of proton plus neutron. Okay, so number of proton plus neutron. That's what we meant by nuclear number, right? So number of proton plus neutron. So by right, if your proton number increase by 1, your nuclear number supposed to increase, what do you call it, by 1 also. Actually, what happened in beta decay, right? In beta decay, okay, that one neutron, okay, that one neutron will split into one proton and one electron. Okay, electron. Okay. So example, right, this one 90, right? 90, right? So 90, right? So if one of the neutron, okay, decays and become a proton and electron, so here supposed to be 89. Okay, 89, right? Okay, when it decreases, it's supposed to be 89. So on top, we're supposed to be 89 lah, by right. Okay, but what happened is this electron is the one released as your gamma ray. Okay, so the electron will be released as gamma ray. So that means you have only one proton. Okay, so see, this is 38. Okay, so you plus one proton, you get 39. Okay, but you must remember, right? This neutron number, so a nuclear number is become 89 because one of the neutron has split. But nuclear number is number of proton plus number of neutron. So what happened? This one proton will add up back into the nuclear number. Okay, so altogether you become 90. Okay, altogether you become 90. Okay, so example lah, to make it easier, right? Okay, this is 38, right? Okay, 38 is number of proton. Okay, so 38 number of proton, and then your nuclear number is 90. Okay, so 90, right? So okay, so we know that the proton is 38. Okay, so your neutron number will be 90 minus 38. 52. Okay, 52. Okay, 52 lah. So what happened is, okay, when it decays and emit beta particles, so one of the neutron will split. So maybe one split means by right is supposed to become 51. Right, 51 lah. So one of them will split into proton, one will split into electron. So this electron will come out as gamma ray. So what happened? Your proton number now will increase. So that means you plus one more proton here. Okay, so that's why it become 39. 38 plus 39. But 39 plus 51, you get back 90 lah. So that's why our neutron number doesn't change. That means what happened? When the one neutron split into one proton, one electron, the electron comes up as your beta particle. So that one proton will add back into your nuclear number. So your nuclear number will remain the same. Because the proton, number of proton, that one proton will add up back, okay, into the neutron, one neutron that is splitting just now. Okay, that's why they doesn't change. Okay, so basically what happens is for beta decay, number of proton increase, proton number increase by 1, neutron number doesn't change. Okay. Now gamma basically has no proton number, there's no neutron number. So what happens when the element decays, right, from X to another element, not to another element, it'll be the same element. Why? Because they have the same proton number, same neutron number. So only thing, the energy will be lower because some of the energy is converted into gamma ray. So example like cobalt 60, right? After decay, still cobalt 60. Okay, it doesn't change to a new element because proton number, neutron number same. But in terms of beta and alpha decay, what they call it, the element will change. Okay, element change. Okay, from here to here, different element. Why? Because they have different proton number, different. Okay. Now we look at an example of question involving this. Now this one is a basic question. Let's say they ask to balance the following equation. So
Raise
this
a question.
Huh?
Question. Yang for gamma ray, right?
Yeah.
What is the apa? Yang macam lambda terbalik tu.
Yeah. Gamma ray symbol macam ni.
Oh, okay.
Yeah. Okay. Now let's say they ask you to balance the equation, right? Okay, you see this 214, this is 4. That means on top here must be 210 lah. Okay, this is 84, this is 82. So you put 2 here. Okay, so 82 plus 2 equals 84. Okay, yeah. Now, so this one, right, you have to balance. So we know that this one is 91. So 84 minus 1, you get 83. So on top here, 214 plus 0, you get 214. Okay, so this one is very easy lah because okay, it doesn't, what they call it, it doesn't change, okay, in terms of the neutron number. And then it's very direct. Okay, yeah. Now, this one, right? They ask you how many alpha and beta particles are emitted when 23290 thorium decays into 20882 plumber. Now they say how many alpha and beta particles. That means this one, right? More than one alpha and more than one beta is being emitted. Okay, so we want to know how many alpha, how many beta. So what you do is first you write the equation. Let's say pH 23290. Okay, decays into plumbum 20882, and then it decays alpha particle and also beta particle. Okay, so you just write this one lah. So we want to know how many alpha. See, yeah? This is 232. If 208 plus 4, you only get 212. So it's not enough to balance. Here cannot plus, here 0 got no effect. So now, first you need to know from 208, right, neutron number to become 232, how much you need to plus some more lah. So you need another balance of 24. Okay, because 24 plus 208 will give you 232. Okay, yeah? Now, so one alpha can only provide 4 neutron number. So in order to get 24, you need 6 alpha lah. Okay, instead of writing 4 to helium 6 times, we write 6 alpha. Okay, actually it's 4 to helium, 4 to helium, 4 to helium 6 times. But I'm just going to write like this, so 6 alpha. So 6 times 4, you get 24. So 24 plus 208, you get 232. So balance already lah. Okay, now how about here? Okay, the bottom one, this is 82. Okay, so the proton number here is 12. So if you have 6 of them, 6 times 2, the proton number is 2. So if 6 of them become 12 lah. So when you add up now, you have 94. It's only more than 90. So how much you have to minus to get 90? You have to minus 4. So that you get back 90. So that means there must be 4 beta. So your answer will be 6 alpha and 4 beta. Now, usually why we do the neutron number first? Because neutron number easy to find out because it is 0. So it doesn't affect. So the only thing that will affect is the alpha particle. So we do this one, then we do the bottom one. Okay. So what you do is first you write out the equation. You write the paranucleide, daughter nucleide, and then alpha and beta. And then you check on the neutron number first, 232. So here 234. So you need to know how much you need to top up to get back to 232. Okay. So if one alpha is 4, you need 6 alpha to get 24. Then you do the bottom one. Okay. Then it's balanced back. Okay. Now example 3. Both alpha and beta particles are produced when 23490N decays into 21892N. How many alpha and beta particles are produced? So same thing lah. So M 2 3, 4, 90. Decays become N, 218, 92, plus alpha and beta. Okay, so this 234, right? So how much we need to get back this 218? So I need another 16. Okay, so I only have 4 here, so I need another 4 alpha. So 4 times 4 will give you 16. So 16 plus 218 get 234. Okay, the bottom one is 92. Okay, so 92. So 4 plus 2 is 8. So you'll get 100. Okay, so how much you need to minus to get back 90? You have to minus 10. So here will be 10. Okay, so answer will be 4 alpha, 10 beta. Okay, 4 alpha, 10 beta. One more example. So B, right? 2, 3, 2, 92 decays into W plus alpha beta. So now I have 232, I have 220. So I need to plus another 12. So 4 alpha is 3. 1 alpha is 4 neutral number, so I need another 3 lah. Right, 3 times 4, 12. So 12 plus it get 232 lah. Okay, how about the bottom one, right? So 90, so 3 times 2, so 90 plus 6. So I have 96. So how much I have to minus, right? So I have to minus 4 to get back 92. Okay, so you put 4 here. Okay, so the answer will be 3 alpha, 4 beta. Okay, 3 alpha, 4 beta. Okay, now sometimes, right, what happens is they give you the question in this format. Okay, in the like, graph like that lah. So this one is a neutron number, this is your proton number lah. So they ask you, what is the number of alpha and beta particle emitted? That means from here, this is the starting, this is the ending. Okay, this is the starting, this is the ending. Okay, you see, this one is much more easier actually, okay, compared to just now. Okay, you don't need to do any calculation. Just remember, right, in alpha decay, right, your nuclear number will decrease by 4. Okay, whereas beta decay, proton number increase by 1. The down one, need to look also in mind. Okay, so you look here, right? Now from here, right, uranium become this one. So you can see, right, from 238 becomes 234. That means your nuclear number decreased by 4. So understood here must be alpha lah. Okay, and then from here to here, your nuclear number doesn't change, still remain at 234. But you can see that your proton number plus 1. So I know this is beta. From here to here, so nuclear number remains the same, but I can see the proton number increased by 1. So this is also beta. Okay, and then from here, decay into here. So 234 to 230, again minus 4. And then from here to here, again minus 4. Okay, so this is alpha, this is also alpha. So that means the answer will be 3 alpha, 2 beta. Okay, so very simple. Alpha, you just look at the nuclear number decreased by 4, you know it's only alpha. Beta, if you look at the proton number only, okay, proton number changing, but nuclear number doesn't change. So you know the beta particle. Okay, so this one is easier compared to the other one. Okay, even though it looks complicated, it's nothing, but actually it's easier. Okay, so from here to here, minus 4, so alpha. From here to here, plus 1, proton number. So beta, beta, so alpha, alpha. So 3 alpha to beta. Okay. Now we look at example of structured question. Now, diagram 7 shows the deflection of 3 types of radioactive emission in an electric field. So, what is meant by radioactivity? So, this will be the answer. Spontaneous and random decay. You can use disintegration or decay of an unstable nucleus into a more stable nucleus. Spontaneous and random decay of an unstable nucleus into a more stable nucleus accompanied by emission of radioactivity. Okay. Next. So what type of radioactive emission is X and Z? So you can see that X is deflected towards negative, Z towards positive. So X will be beta particle. X will be alpha particle, Z will be beta particle. Okay. So X is alpha. Beta. Beta particle. Okay, now give one reason why the deflection of Z is more than X. Okay, why the deflection of Z is more than X. Okay, so why Z is more than X? So that means because beta has smaller mass. Okay. Then so complete the equation by reaction by writing the appropriate number in the box provided. So they ask you to balance. So 23592. Okay, so this one, the top one is balanced, bottom only. So it will be 92 minus 36. So 56. Okay, 56. Okay, now 26. A radioactive source emits two rays, P and Q are placed in the front of electric field. And the radioactive part is shown in diagram 1. So name the material for container X. Okay, so usually the one we use will be lead. Okay, because lead can block gamma ray. Okay, lead can block gamma ray. Next, complete the sentence by underlining the correct phrase in the box. So P is what? So P, you see that it's deflected towards the positive plate. So P will be electron. Okay. Now, why the deflection of P is greater than Q? Okay, why the deflection of P greater than Q? So why P greater than Q? Because P has smaller mass. Okay. Next. Now, diagram 6.1 shows the nuclide notation of an element. So table 6.1 shows equation of the decay process.
Sir,
Yeah.
sorry sir, but for B2 they want the reason from B1 or A1?
Oh yeah. B2
B2.
Yeah, B2
Just now
reason
your
means,
answer.
oh P just now I
Supposed to
said,
be beta, right?
yeah, P is beta. That's why
So reason
reason because it's
talking
negatively
about
charged.
mass or natively.
Mass supposed to be this one. See, sorry. Okay, give the reason, right? So you can say because it's negatively charged.
Okay.
Okay, and then why deflection of P is greater than Q? Then you can say P has smaller mass.
Okay.
Now 27. Now diagram 6.1 shows the nuclear notation of an element. 6.1 shows the equation of the decay process. Okay, so what is meant by nuclear number? So nuclear number is number of proton and neutron. Okay. B, By using both equation in table 6.1, calculate the difference of nucleon number between uranium and thorium. Okay, between uranium and thorium. Okay, so here will be 238, here 234, right? So minus lah. So 4. Okay. And then radium and radon, same lah, 226, 222, also 4. 4 also. Okay. By using both equation, calculate the difference in proton number. So 92 to 90, 2 also. 88 minus 88, also 2. So here 2, here 2. Okay. Now, based on the answer, complete the sentence below. So when alpha decay, the nucleon number decreased by 4. And the proton number decreased by 2. Okay. Next. Diagram 6.2 shows a radioisotope which emits alpha particle. So, complete the path of the alpha particle when it enters a region between two metal plates. So, alpha will be deflected towards the negative. Okay. So, it doesn't matter whether it touches or doesn't. Okay. So, okay. So, give one reason, right? Why it deflected that way, right? Because positively charged. Okay. Okay. 27. Now, polonium nucleus emits alpha particle and gamma ray to become a plumber nucleus. So complete the decay equation of polonium by writing the appropriate number in the boxes provided. Okay. So here will be 4. So here will be 206. 82. So here will be 2 lah. Okay. Now, polonium nucleus is placed in front of the neutrophil. Okay. Draw the path of alpha particle. Straight and deflect number. Okay. Oh yeah. So one more is gamma. They want gamma also. So gamma will travel straight. Okay. So explain why, right? So you say alpha positively charged. Gamma will be no charge. Okay. Okay. C we haven't learned yet. Okay. We haven't learned yet, so we just leave it for a while. Okay. We look at number 29. Okay, 29 this one. Now, strontium 90 is a radioactive isotope that emits beta particles, and it decays. The nuclear equation shows the decay. So find the value of A. So A will be 90 and then B will be 39. Okay. 3 nucleus are represented as shown. State and explain which nucleus are isotope of the same element. Okay, isotope of the same element. Okay. So answer will be X and Z. So reason will be same proton number and then different nucleon number. Okay, same proton number, different nucleon number. Okay. Now in a lab, vacuum chamber, some current carrying coils produce a very strong magnetic field near a source of alpha particle. So figure 10.2 shows the arrangement. So in the shaded region, in figure 10.2, draw a possible path for the alpha particles in the magnetic field. Okay, state and explain. Okay, so use your Fleming left hand rule. Okay, so FBI. So your magnetic field is going into it, right? So magnetic field must point inward because going into, okay, going into, and then alpha is moving this way. You can see alpha moving this way, right? Alpha moving this way. That means your force is upward. Okay, so that means your finger must pointing towards inside this way. Okay, use your Fleming left hand rule, so this way. Okay, and then your alpha is moving here. You can see the alpha moving here. Okay, so magnetic field is going into, that means the force is upward. Okay, so use your left hand. So reflected upward. Okay, so to explain the effect on this part of reversing the current in the coil. Now, when you refer, when current passes to a coil, it become electromagnet. So when you change the direction of current, you change the direction of magnetic field. That means if just now going in is just now the magnetic field going in, right? So now the magnetic field is supposed to be going out. Okay, going out. Okay, because you reverse the current, that means you reverse the direction of the magnetic field. So if just now the magnetic field going in, so that means now the magnetic field must be going out So in order, when the magnetic field go out, that means you will deflect downward, opposite of just now So just say deflect downward. Okay, downward. Okay. Okay, last example. Okay. Now, radium-226 decays according to the equation below, emitting alpha particles. So, how many protons are there in the nucleus of radium? So, how many protons they have? So, the answer will be radium, right? So, 88. How many neutrons are there in the nucleus of radium-226? So, 226 minus 88. Okay, so minus only. Okay, Now, next. From the equation, determine the proton number and nucleon number of particle X. So the proton number, right, will be 2. Nucleon number will be 4. Okay, 4. Okay. And then they say deduce the nature. Now, when they say deduce the nature, that means what is particle X? Okay. You don't write particle X is positively charged. Okay. You must say particle X represent what? Not the characteristic. Okay. Not characteristic of particle X. Okay. Positively charged the characteristic. So but actually what is particle X? The answer will be alpha particle. Okay. Alpha particle. Okay, alpha particle. Okay. Don't write helium. If you write helium, nucleus can. Okay. Because it's not an atom. It's just a nucleus without the electron. Okay. So alpha particle or helium. Best answer will be alpha particle. Okay. Okay. Now we look at detectors of radioactive radiation. Now, for your syllabus, okay, turn from the besides the next notes. Okay. Half-life. Okay. Now, detectors of radioactive radiation. Now, for your syllabus, what they want is they want you to know the detectors and what they call it, what type of radiation can be detected. They don't actually ask the working principle lah. But anyhow, I just say a bit on the how it works. Now, the first one we call it photographic plate. Now, photographic plate basically uses a film. If you remember camera, right, before digital camera, we have the film. Use a camera using the film to take photos. That film actually is the what we're talking about, the film. So the film can be used to detect radioactive radiation. So what happened is this film, right, is coated with a chemical argentum bromide. Okay. So what happened when the radiation hits the what do you call it, the film becomes darkened. It becomes dark lah. It's going to become dark. Okay. So the darker the film, the stronger will be the radiation. Okay. The darker the film, the stronger will be the radiation. So it's like this. This is the photography plate. Okay. So here, so usually what they do, they wear like a badges like that lah. Okay. They wear like a badges. Okay. So okay, example like this lah. Now let's say if you have a film. Okay. So this is a film. Okay. So let's say so this one is so the bottom part here. Okay. Let's say one third is covered with paper, and then this one is covered with aluminium. Okay. Aluminium with few millimeter thickness lah. Now let's say if you have a radiation. Okay, you have a radiation. Okay, let's say P lah, you want to know. So what happened when the radiation pass through, you see that okay, this part of the film and only this part of the film is darkened. That means this part not darkened, this one not darkened. That means what happened? We know that the radiation cannot emit, can be blocked by paper. So we know this is alpha particle lah, alpha particle. Okay. Now let's say you have another radiation Q. So when radiation pass through, what happened? You see that the top one is darkened, and then the bottom one here near the paper at the back paper so darkened. But the middle one doesn't get darkened. So that means we know that radiation cannot penetrate aluminium with few millimeter thickness. So that means this is understood to be beta particle. Let's say you have another radiation S, right? So all the film is darkened. That means we know that it's gamma, okay, because aluminium with few millimeter thickness it can enter. So we know it's gamma ray. Okay. So this type of detector, the photography plate, can detect all alpha, beta, gamma. Okay, alpha, beta, gamma. Okay. Okay, now. Okay, the next one we call it electroscope. Now, this electroscope can be used to detect only alpha and beta. Okay, alpha and beta. So what happens is, okay, let's say you have electroscope which is positively charged. Okay, so you bring a radioactive source here. You bring a radioactive source. Okay, so when you bring the radioactive source will emit radiation. Okay, so will emit radiation. Now, what the radiation will do is, the radiation will ionize the air particles into positive and negative ion. So that means the radiation from the radioisotope, okay, radioactive material will ionize. So the air particles will be ionized into positive and negative. So this electroscope is positively charged. So what's going to happen is, the negative ion will be attracted towards the electroscope. Okay, so the negative ion will be attracted. So the negative ion attracted. So what happened? It causes the electroscope to be neutralized because there's a negative ion now. So what happened? The electroscope will be neutralized. So because of that, the deflection will start to decrease. Okay, so the deflection will decrease. Okay, so deflection will decrease. Okay, deflection will decrease. Okay, so this one, right, can only detect alpha, beta. Gamma cannot, because gamma, the ionizing power is very low. Okay, so gamma ionizing power is very low. Okay. Yeah. So okay. Next. Okay, this one we call it the spark counter. Now the spark counter. So the spark counter, right? It can only be used to detect alpha and only alpha only. Okay, so it can only be detect. It can be used to detect only alpha particle. Okay. So why? Because alpha particle has strong ionizing power. So what happens is, right? So there's a wire gauze here and then there's a thin wire here. So the wire gauze and the thin wire will be connected to a high voltage power supply. So there'll be a strong electric field between the thin wire and the wire gauze. So what happens is when the radioactive source emit radiation, so what it's going to do is it's going to ionize, right? So it's going to ionize the air particles into positive and negative ion. Okay, so there'll be positive and negative ion. So what happens is the negative ion will be attracted towards anode, the positive ion attracted towards cathode. Okay, so the negative ion towards anode, positive towards cathode. So what happens is, right? Okay, so when the ions are moving, right, in the opposite direction, they experience collision with the ions, among the ions, and also the air molecules. So because of the collision, there will be spark. That's why I call it spark counter. Okay, so okay, there will be spark counter. I call it spark counter because it will form spark there. Okay, when the ion moving in the opposite direction. Let's say the positive move up, the negative goes on, right? So they will experience collision. So they will collide with air molecules. So because of that, what happened? There will be spark produced. Okay, so I call it spark counter. Okay, so there'll be a counter here to calculate how many spark made, let's say in 1 minute. Okay, so this one can only use for alpha because alpha has strong ionizing power. Okay, alpha has strong ionizing power. Wait, let me check the spark.
We can see the mesh.
You can see this video, right?
Can.
Okay. So this is a spark counter. So you can see the wire gauze and the thin wire. Okay, so the wire and thin gauze. So when you see when you when you bring the radioactive source, you see there'll be a spark here. Okay. So what happens, the radiation will ionize, okay, ionize the air molecules into positive and negative ion. So let's say when the positive goes up, okay, so make more ions, right? So when they move, what happens, they experience collision with each other. So that's why it becomes, that's why there's a spark there. So let's say the positive moves up, negative goes down. Okay, so that's why you see there's a spark. Okay, so you can see here, okay, this is the wire gauze. Okay, and then at the bottom here will be a thin wire. Okay, so they are connected to high voltage power supply. Okay, so what happened? The radiation will ionize the air molecules into positive and negative. Okay, so let's say if the cathode is on top, that means the positive will go up, the negative will go down. Okay, so the electron goes up, the positive goes up. So they will experience collision. Okay. Okay. So this one can only detect alpha. Gamma not suitable. Now next we look at Geiger-Müller tube. Okay, now Geiger-Müller tube is the most famous, okay, detectors used because it's easy to handle and it can detect alpha, beta, gamma. So basically what happens is for GM tube, right? Okay, there'll be a, okay, a thin wire here. So the thin wire here is connected to the positive terminal, and then the body, the body is the, okay, body here will be connected to the negative terminal. That means the body here will become a cathode, okay, and then the window here must be very thin so that can alpha, beta, gamma, so that alpha also can enter. So then inside it there's an argon gas at low pressure. So what happens is, so let's say when you bring the radioactive source, so the radioactive source will emit radiation, okay, emit radiation. So when the radiation passes through, what happens, it will ionize the what they call it, the argon gas into positive and negative ion. So what's going to happen is the positive ion and the negative ion will start to move in to their respective electrode. Let's say the negative will move towards the positive will move to negative. That means in this case, okay, let's say this is your thin wire, right? So your thin wire is positive, and then the body here, right? So the body here is negative. So what happens? Let's say you have positive, negative, positive, negative, right? So the negative goes up, the positive goes down. Okay. So what happened? Okay. So every time the ion touches the electrode, there'll be a current pulse. Okay. Every time it touches, there'll be a current. So it'll be something like a current pulse, something like this. Okay. Now, why the current is not continuous? Because the moment the electron touches, there'll be current. If the electron doesn't touch the electron, it won't be a current. So you won't get a constant current like this. Okay. So every time it touches the electrode, there'll be a current pulse. So call it, okay, we calculate how much current pulse. Okay, so pulse of current made in 1 minute, let's say. Okay, so it's almost same as your what do you call it, spark counter, but only this one is measuring the current pulse. The other one is measuring spark. Okay, this one measuring current pulse. So every time the ion touches the electrode, there'll be a current pulse. Okay, so now one more thing about GM tube lah. Okay, what happened is GM tube, okay, is very sensitive in such a way that, now let's say if you bring a radioactive source, okay, if you bring a radioactive source, now if you bring a radioactive source, let's say the counter here record, okay, let's say 250 current pulse per minute, example only. So what happened when you remove this? By right, this one's supposed to go to 0, right? But it doesn't go to 0. Maybe you go to something lower, let's say 80. Okay, 80. Now, why it doesn't go to 0? Because this GM tube can also detect what we call it as background radiation. Okay, it can also detect what we call it as background radiation or background reading lah. Now, background reading is made from naturally present radioactive material on Earth. Okay, example like stone, sand, fossil, and all this. Okay, so they do emit radiation, but it's not very strong. Okay, it's not very strong. So this radiation, okay, can be detected by GM tube. So I call it background radiation. And then also naturally, and also from the sun. Okay, from the sun, we call it cosmic ray. Okay, it's a charged particles. Okay, charged particle from the sun. Okay, so when it enters, what happens? It causes this ionization. So we call it cosmic ray. Okay, so background reading is from naturally present radioactive material on Earth and also because of cosmic ray. Okay, so what happens is, if you want to get your actual reading, what you must do is, you have to take your background reading. Okay, let's say your background reading is 250, right? So, and then let's say your background, your reading, right? Your reading is 250, you minus your background reading. So then you get actual reading. So this is how we measure the reading, okay, using a GM tube. So you must have the reading recorded minus the background reading will give you the actual reading. Okay, so this is what they call it, GM tube. Okay, GM tube. So GM tube. Okay, so this one is a thin mica window lah. Okay, it must be very thin. So let's say this is all the argon particles. So what happened? Okay, so when the radiation passes through, it will ionize the argon to positive and negative ion. Okay, so let's say each time the electron, right, touches the wire here, what happened? There'll be current pulse. Okay, so there'll be current pulse. So each time the ion touches, there'll be current pulse. So there'll be a counter here. So the counter will calculate how much current pulse made in 1 minute, let's say. Okay, so that's what we mean by, okay, so this is what we mean by current pulse lah. Okay, so every time the radiation passes through, it will ionize. So then the electron goes to the wire here. So every time it touches, there'll be a current pulse. Okay, so you can detect alpha, beta, gamma. Okay, now the last one we call it as cloud chamber lah. Okay, now cloud chamber can also detect alpha, beta, gamma, but this cloud chamber is not that famous because it's not portable lah. It's not portable like your GM tube. So GM tube is more portable. You can bring, you can like a scan, kind of thing. But what do you call it? Cloud chamber, no lah. Now basically a cloud chamber, right? The important part is, okay, you have the down here sponge, and then you have the dry ice, and then you have a metal plate here, dark in color lah. And then you have the okay, there's a what do you call it? Felt, it's a cloth. Okay, this cloth is soaked with alcohol. Okay, and then you have the radioactive substance. So now what happened is, right, so this radioactive substance will emit radiation. Okay, will emit radiation. Okay, so when you emit radiation, what happened? It's going to ionize. So what happened? The air particles will be ionized into positive and negative ion. So the air particles will be ionized into positive and negative ion. Okay, so the air molecules will be ionized into positive and negative ion. Okay, so what happened is, okay, when the radiation, right, when the radiation travel, this one, alcohol, this alcohol is exposed to room temperature on top. So on top is room temperature. So alcohol is exposed to room temperature. So we know that at room temperature, what happens to alcohol? It evaporates easily. So it starts to become gas lah. So this alcohol in the form of gas will start to spread out. Okay, so they start to move lah. Okay, the alcohol will start to spread out. Now, as the alcohol goes, what happened? It goes down here. When it goes down here, first, down there, there's a lot of ions. So what happened? All the alcohol will start to stick onto the ions. So they start to stick. Okay, so the alcohol will be sticking onto the ions. That's the first part. Now, the second part is, okay, the region down here is very cold. So it's very cold. What happened to alcohol? From gas, it will change back into liquid. So what happened? The alcohol not only stick to the ion, but it start to experience condensation. That means it will change back to liquid. So when it change back to liquid, what happens is you'll be able to see white lines like this. So these white lines we call it as misty track. Okay, you'll be able to see white lines like this. Okay, we call it as misty track. So it'll be like this lah. Okay. So you form white lines like this. Okay, we call it misty track. Okay, misty track. Okay. So that's why it must be black in color. The metal plate black in color so that you can see the white lines. Okay. So the felt, okay, which is so we alcohol is supposed to be on top here. Okay, so we alcohol. So the alcohol will experience so alcohol will evaporate. On top it evaporate because room temperature. So what happens is when room temperature evaporates, and then when it start to go down, what happens? It will stick onto the ion formed by the radiation. Okay, so because of that, you can see the misty track. Now, what they will ask you is they won't ask you how the working principle, as I told you earlier, but they will ask you why alpha, beta, gamma have different pattern. Now, if you look at alpha, right? Alpha, the lines are straight, but beta a bit crooked. Because alpha, why the lines are straight? Because they got bigger mass. Okay, bigger mass. Okay, they got bigger mass lah. So when a bigger mass, what happen is when they travel, they are not easy to deviate. Okay, but beta can deviate easily lah because of collision. They start to move haywire like that. Okay, and then one more thing, you see that alpha got more lines. Okay, first is straight, right? So among them, alpha will have the most line. Okay, most number of line. Okay, why? Because it have a strong ionizing power. Okay, strong ionizing power. Okay, compared to beta lah. Gamma will have very less. Gamma will be that dot dot like that. Okay, because gamma the ionizing power is very low. Okay, so all these are using ionizing power. Okay, so what do you call it? Except for photographic plate. Okay, photographic plate is just chemical reaction. Okay, but spark counter, GM tube, okay, what do you call it? Cloud chamber, all these are using the concept of ionization. Okay, that means the ionizing power of the radiation to detect how to detect the radiation. Okay, so the only thing that can detect alpha, beta, gamma is only cloud chamber, GM tube, and also what they call it photographic plate. Okay, alpha, beta only is electroscope. If alpha only spark counter. Okay. Okay. Now we look at example of structured question in terms of the detectors. Now we look at number 21. This is a past year question. Now diagram 4.1 shows a geologist using a Geiger-Müller tube and a counter to detect the existence of radioactive material in the rock. So diagram 4.2 shows the reading of the counter when the Geiger-Müller tube is not close to any radioactive material. So diagram 4.3 shows the reading of the counter when the Geiger-Müller tube is placed close to a rock that contains a radioactive material which emits gamma ray and beta particle. Okay. So what is beta particle? So beta is fast moving electron. Okay. So what causes the reading shown in the counter in diagram 4.2 lah. Okay, 4.2, right? When it's not close to any radioactive material, that means you get 150, right? So this one call it background reading. Okay, so background reading. Okay, background reading or background radiation. Now, a sheet of aluminium is placed between the radioactive material and the Geiger molecule in diagram 4.8. So what happened to the reading of the counter? Okay, so the reading of the counter, so this one emit gamma and beta, right? For 30 lah. So if you put aluminium, what happened? Only the gamma can enter, the beta cannot. That means your reading will be decreased. Okay, so reading will be decreased. Okay, so reading will decrease. So because beta particle will be blocked by aluminium. Okay, aluminium. Okay. Now, the decay equation, the decay of uranium found in the rock can be represented by the equation below. So calculate the calculate the value of x and y lah. X and y. So we can see here, this is 92, this is 82. Okay, we do the top one first. So I need to add another 32. Okay. So that means x must be 8 lah. Okay. Okay, this one I do like spontaneous, right? But in exam you have to show the working lah. Maybe you can write, okay, 238 equals to 206 plus 4x. Okay. Actually, without doing this, you can know already, right? Because we, okay, we do it mentally like that, right? Okay. But in exam, because you need to show the working, that's why I have to show like that. Okay. So x will be 8. And then for the other one, 92 equals to 82 plus, okay, you already put 8 there, right? 8 times 2, 16 minus y. Okay. So y will be 82 plus 16 minus 92. Okay. 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 Next, Now, in an experiment to find the range of alpha particle in air, the apparatus in diagram 8.2 is set up. So state one suitable detector to detect alpha particle. Okay, so to detect alpha particle. So this one you can write lah. Anything what GM tube can, what you say, GM tube lah. GM tube. Okay. And then state the cost of the count rate at the distance of 9 cm from the source. Okay, 9 cm from the source. Okay. Okay, you see that this experiment actually we want to, what they call it, we want to study the range lah, okay, of a type of radiation, okay, alpha particle. So you want to see how far alpha particle can travel. You see that initially was when it's 1 centimeter, the reading is 61, then start to decrease. After that, you will see that the reading dropped drastically, but it becomes something like a constant. That means your reading is like, okay, it drops, then after it becomes something like constant, 20, 19, 21, 19. Okay, So meaning, after 5 cm, you cannot detect alpha particle already. After 5 cm, you only detect background reading. So background reading fluctuates because it depends on the material that emits radiation. So it fluctuate, but it will not run much, 20, 19, like that. So that some sort of like an average value will be there. Okay, so the reading will be fluctuate. So this background reading. That means after 5 cm, we only detect background reading. That means from here we can see that alpha particle can only travel 5 cm. Okay, maximum for this experiment. Okay, so okay, state the cause, the current rate at distance of 9 cm, right? So that means the answer will be background reading. Okay, background reading or background radiation. Okay, now estimate the count rate that is only due to the source at the distance of 2 cm. Okay, at 2 cm, right, what happened is, this is 562. 562 is actually the reading of the source plus the background. So you have to minus the background. So how to minus? What you do is you plus everything. You take something like average divide with 4. Okay. Hello. Yeah. Ada. Sekejap Okay, yeah. So 20 plus 19, 21, 19. So I think you get so you get 105. Okay, so 105. So 562 minus 105. So 4.7. Okay, 457. Okay, 457. Okay, hold on for a while. I need to go see someone for just for a while. Uh, okay, so we continue back. Yeah. Now, using table 8, what is the maximum distance alpha particle can travel? Okay, so what is the maximum distance? So from here we can know that it's 5 cm. Okay, 5 cm. Okay, 5 cm. So 5 cm. Okay, so justify your answer. So they ask you to state what is your answer. Justify your answer. Okay, so why you say 5 cm, right? Okay, so you say after 5 cm, the reading drop. Okay, the reading drop drastically. Yeah. Okay, so the reading drop drastically. Okay, reading drop drastically. After 5 cm, the reading drop drastically. Yeah, that means drop a lot. Okay, drastically. And then 2 points, right? Okay. The detector detects only background reading. Okay. The detector only detects background reading. Okay. So 2 marks lah. So get 2 points. So after 5 cm, reading drop drastically, and then the detector only detects background reading. Okay. So okay. So this one, right? Your background reading sometimes you have to take average lah. Take average. If not the same, you take average. Okay. So your actual reading is your actual reading is the reading that you record minus your background reading. Okay. So background reading sometimes it fluctuates. It doesn't stay constant. Okay. Okay. So that's all. Okay. The half-life I will continue next week. So next week we'll still use the same notes for a while, and then we start with the new notes. Okay. So that's all for today.
Thank you, sir.
Thank you, sir.